Hi all, we're going to be starting this review video with talking about matter and measurement. So starting off here, these are definitions. Matter has mass and volume. Volume occupies space. And mass is amount of matter. So those are definitions. This is kind of that first day when we started covering material. U matter is the sign in the classroom. Because you have mass and volume, you are by definition matter. Volume is how much space something occupies. So those kind of keywords is like we're thinking about how much space, how big an object or a piece of matter is. And then mass is the amount of matter. When we moved down here to, we started talking about matter, and then we followed up with how we measure things. In science. And so in everyday life, in American life, a lot of times we talk about pounds and feet. But in chemistry and science, we use International System of Units, which is SI units. And those units include grams, liters, seconds, Kelvin, or Celsius. It's really supposed to be Kelvin, but in the lab most of the time we're using Celsius. Grams, liters, seconds, Kelvin, and meters are our base units in chemistry. If you think about the fact that a paperclip has a mass of 1 gram, the mass of an orange, well, it's probably going to be somewhere between 100 and 200 grams. Most likely, 150 grams is what I would estimate that at. Reasonable estimate of a mass of a pencil, well, again, we're talking about 5 grams, maybe 5 paperclips kind of making up that total. Coming on down here, when we measure something, we want a tool that measures both precisely and accurately. But if we want to get kind of more into the nitty-gritty of what that means, well, a tool that is measuring over and over and getting the same number, that tool may be precise. It's not necessarily accurate, but a tool that is measuring and getting the correct number is an accurate tool. So we have precise tools, we have accurate tools, and ideally we want tools that are both precise and accurate. Well, how does precision kind of come out in the world, and what does it look like for us? So tools, especially electronic tools, are sold as being precise at a particular level. And so when we get an electronic scale or an electronic measuring tool, it will be accurate to the number that we see. If we have an analog tool, however, like a graduated cylinder, like the old school scales that we used to measure the mass of Oreos, or like a ruler, we're going to have to measure that ourselves. And when we measure ourselves using an analog tool, we always measure one place beyond what we can see. So we add this estimated place. And that ends up telling us, because that's the rule everyone operates off of, when I see a number that says 1.55 centimeters, I know that was either measured using a digital tool that was precise to that level, or was measured using an analog tool, and that final digit is estimated, and that gives me a higher degree of confidence in the previous place. So I'm going to draw some examples here on the piece of paper, and we also have these examples on the screen. So give me 1 second, we'll look at this example. Alright, so let's go ahead and practice real quick with this drawing. It's a little bit easier to see when I make things a little bigger, so we're going to start with this and then look at the examples on the review packet. So when I'm measuring, if this is the ruler, this first one up here that I'm using, if I'm measuring the length of this pen cap, most folks say, yeah, okay, I get that this pen cap, well, between 1 and 2, it looks like it's just under halfway. So it's, 1.4 centimeters. Let's say this is centimeters, although obviously it's not quite perfect there on the drawing. So we'd say it's 1.4. And, some people might say, well, it actually looks like 1.3 to me, right? But we know that it's between 1 and 2, and that it's a little bit under halfway. So notice the last markings we could see here were in the ones place. And so I wrote the 1, I could see that one, literally. And then I estimated how far, if this is 1.0 and this is 2.0, how far did I get along this line where I'm going from 0 to 9 here and then rolling over with the tenths to 2. So if I was right here, this would be 1.9. If I was right here, this would be 1.1. And I'm estimating where along this scale I am. Halfway is 1.5, and I'm just under halfway, so I'm about 1.4. So most folks, I'd say, maybe 80% of us get that no problem. The difficulty comes when we have more markings. And so on this drawing, I've still got 1, and I've still got 1 and 2. But I also have these tenths place markings. And so the deal is, the underlying principle is still whatever the smallest markings are, you're going to have to estimate between them. So this is 1 and this is 2, which means the smallest markings I can see are in the tenths place. This line is 1.1, this line is 1.2, this line is 1.3. And I can see that my pen cap is going between 1.2 and 1.3. And so I'm going to go ahead and write 1.2, and then I'm going to estimate where it is between 0.2 and 0.3. So this is 0.2 and this is 0.3. And just like up here, there was a sliding scale where we went from 0 to 10 and we rolled over at 10 to the next line. Here, we've got the same thing where we've got 0.2, we've got 0.3, and right next to 0.2 is 0.21, and in the middle is 0.25. Very close to 0.3 is 0.29, and then at 0.3 it rolls over. And so when we are measuring on this scale or on this, ruler, we're going to have to estimate the final place. And so, I want to make sure that it's lined up right. And I'm going to say, okay, well, look at that. That is pretty much dead set in the middle. So that's 1.25 centimeters, all right? And the really amazing thing about using a more precise analog tool is that now, whereas on this previous measurement, I might have said, oh, well, it may be, maybe it's actually pretty close to 1, or maybe it's pretty close to 2, because I don't have that high of confidence in the last estimated number, right? Because we're estimating that final number, and we can get pretty darn good. But because it's estimated, you might not be quite as confident. Here, well, some people might say, I actually see 1.23 or 0.24 or 0.25, 0.26, but there's no question that it's 1.2, right? And so if we have these smaller markings, we're still estimating between them, just the same, no matter whether we're looking at markings in the tenths place or in the hundredths or in the tens. But it just gives us a little bit more confidence in the numbers. So if we look at these examples here, this line is going to be measured to the tenths place. I moved it over a little bit. I'd edited it and thought it was all lined up, but you saw me moving it just a few moments ago. So this line is coming just a smidge past 2. So I'd call that 2.1. And this graduated cylinder here, we zoom in and look at it. Well, I've got 5.5 there, 5.6, 5.7, and 5.8. It's between 5.7 and 5.8. Looks like it's either quite in the middle. I'd say it's a little bit closer to 5.8 than in the middle. So that would be 5.78, right? We'd have that hundredths place. Similarly here, I take the 100, 100, and 32. And then these markings are in the tenths place. So once again, okay, this is 132.1, 0.2. It looks like it is dead on that 0.2. And so I'd indicate that there was a 0.2 line and that it was not just being estimated as between 2 and 3 somewhere. I'd show, hey, that 0.2 line is there by saying it's 132.20 grams. So when you're measuring, it's important that we measure to the correct level of precision. That is in your old quiz from this unit as well. Scientific notation. Why do we use scientific notation? Because we are dealing with very, very large and very, very small numbers. This is scientific form because we have a number between 1 and 10 multiplied by 10 to a power. So a number between 1 and 10 multiplied by 10 to a power. This number here is in standard form because it's a normal looking number. Remember, if we have a positive exponent, that means we are multiplying by our exponent, so by 10, 20 times. So that's going to be a massive number. Whereas here, a negative exponent means that we are dividing by 10, 20 times. So that's going to be a tiny number. All right. We want to be able to go both from scientific to standard and standard to scientific. So I'm going to check those out and then also use exponent laws here. So since we're going to be looking at the paper here, I'm going to go ahead and make it a little bigger. So for our first problem, we are going from 5.67 times 10 to the 6th, and we're taking that number and writing it standard. So remember, when we write something in standard notation or taking standard to scientific, it's the same number. So first thing I'm going to do, well, this is positive. That's the first thing. Figure out if it's positive or negative, because that's going to tell you whether you're multiplying or dividing. Positive, so I am multiplying by 10 6 times. I'm multiplying by 10 6 times. So how I do that, I want to move this decimal because I'm multiplying by 10. I multiply by 10 once, I'm going to get 56.7. If I multiply by 10 twice, I'm going to get 567. So I'm going to go ahead and keep moving that decimal a total of 6 times. 1, 2, 3, 4, 5, 6. And then I'm going to backfill these spots with zeros and rewrite so that it's nice and neat. Great. So 5,670,000 is the same thing as 5.67 times 10 to the 6th. If you were multiplying by a negative integer rather than moving the decimal to make the number larger, you would move the decimal to make the number smaller. All right, next one, 8,780,000. And we're going to go ahead and find the decimal first so that we can move it to get our number here. So remember, the decimal is always by the ones place. I'm going to go ahead and move it 1, 2, 3, 4, 5, 6. My number is 8.78 times 10, and move the decimal 6 times here again. And it's going to be positive because for 8.78 to be 8 million, we need to multiply by tens, not divide by tens. All right. Last thing are the exponent laws. If you need more problems on these, remember scientific notation is in Unit 1. We do have other problems that show it going to small numbers, so check that out if you'd like some more practice on those. Exponent laws. So the long and short of exponent laws, if you multiply by something that has the same base, you can add your exponents. So this becomes 10 times 2 plus 3, 10 to the 5th. Alternatively, if you divide by something that has the same exponents, you can subtract, and so this would be 10 to the 2nd. Running a little close up to time here, so want to just make sure that we hit both of those underlying concepts. When you're using exponent laws, when you're using something in scientific notation, treat all the numbers the same, and when you hit something that's base 10, remember the 2 rules, which is that if you multiply something by, another number that's base 10, you can add your exponents. And that if you divide 2 numbers that are base 10 or have the same base in general, you can subtract your exponents. So these are 2 examples to try and help you solve those last couple problems in this first section of the review packet. Hope it helps on matter and measurement. Bye.